Hi everyone, thank you so much for coming by. I'm not sure what channel you've read this through, but this is ACM. The two of us here represent the ACM chapter at NYU, and we're really thrilled. I'm going to let him introduce himself. We're really thrilled to have Dr. Desmond Fitzpatrick. Please welcome.
Hey folks, so this will be a pretty informal seminar. Before we start, let me just do a quick, how many people here are computer science majors? Probably about half. How many people know what Moore's law is? How many people know what complexity theory is? Okay, so it's a pretty knowledgeable audience. A lot of the time it's like one guy. Okay, so I'm here to talk about quantum computing. I'm here, I work for IBM. I basically spent my entire career pretty much working for IBM. First half of that career was working in semiconductor development in a place called East Fishkill. And at that time, East Fishkill was pretty much the center of the universe when it came to Moore's law, right? We had, the Wii chips were built there, Microsoft Xbox chips, I mean, you name it, everything was being built there. Second half of my career revolves around what I do today, which is we build very large machines, we build supercomputers, and we want to make sure those supercomputers stay up and running, so what we call resilience, right? So I'm basically the resilience manager for these days for System Z, but in the past, System P, which is our supercomputing arm. Okay, so let me get straight to it. Anybody know what this is? You can raise your hand, I'll pick it. Who wants to answer? Yes, sir. It's a quantum computer, right? Looks a little bit different, right? And I'll explain, you'll see a little more what it looks like when I get down further into it. Everybody can hear me, yes? Yeah. I'll try to stay out of the way so when people who are watching online. Okay, this is an early version, Colossus, right? First electronic digital programming computing device. What was this lady called? Programmer. Not a programmer. I heard somebody else? Computer. A computer, right. That's where it came from. Ladies who used to compute because men were too whatever to do it, right? That's what it looked like then. This is what a quantum computer looks like, right? We're sort of at the same kind of development here. This is the central, core, if you want, of the computer. We'll look in a little more detail, but just to show you what it looks like, right? Maybe if you could actually just click the page, we'll get to the next page, right? It'll be just easier. Okay. Next. Okay, well, here's roughly the agenda I'll go through. I'll do it my own particular way, but motivation, the basics of quantum, anatomy of a quantum computer, programming, right? Very important. The Q experience, the network. Since you're mostly students, we won't talk a lot about the business impact or any of that kind of stuff. How to get quantum ready, and then Quantum One. How many people know anything about quantum computers? Not too many. Okay. So we kind of know where we're going to go next. All right. Okay. This is the most famous. One second. Just pause. Pause it. Do it. You tell me. Okay. Okay, we're resuming post our little pizza break. Okay. So this is a very famous picture in 1927, the Solvay conference, when all the famous quantum people involved in quantum mechanics got together. And so we're going to have a little contest to identify how many people could identify all the people here. But I think we have a volunteer who's going to explain a bunch of them. Sir, you want to introduce yourself and just kind of give us some pointers to some of these famous people?
Sure. Hello, my name is Edison. I'm going to start with
Make sure the camera can see you. Okay.
This Max Planck, Marie Curie, Lawrence, Einstein, and I don't know any of these.
The guy in the middle, right there.
Dirac.
Dirac.
De Broglie, Bohr.
Yep.
Schrödinger.
Schrödinger, yep. And
Maxwell.
And there's Heisenberg. And Born. Right. Fantastic. Let's give him a round of applause. That's fantastic. All right. So what's interesting about it? Know anything unique about Marie Curie? Anybody want to comment? Pardon? She is one of only 3 people who've ever won the Nobel Prize twice, right? Poor Einstein only won it once. Anybody know who the other 2 are? Pardon?
John Bardeen.
Bardeen and I didn't hear that, but Sanger from medicine, right? But in terms of physics, Bardeen and Marie Curie. She won physics, chemistry. Okay, next. Okay, so they were puzzling over, so the amazing thing about this is I think it's 17 Nobel Prize winners in this photo, right? Remarkable. Okay, next. So, this is the equivalent for quantum. This was organized by an IBMer by the name of Charlie Bennett. And MIT, 1981, where is he? Richard Feynman is, there's Richard Feynman, the famous Richard Feynman, right? I was going through this and I had forgotten to mention this IBMer, what's Ralph Landauer, and this guy in the audience, this was at MIT, said, "You forgot to mention Ralph Landauer. And by the way, I took that photo." So the guy in the audience actually took that photo in 1981. His name is Charlie Bennett, and he's a very famous quantum physicist. He actually is an IBMer. I had lunch with him about 2 weeks ago. So he's very impressive. We'll talk about some of his discoveries as part of quantum. Okay, next. Okay, so Richard Feynman got the whole thing going in 1981. Actually, if you look at the rigorous record, there are kind of other people who hint around before it, but Feynman was so emphatic and so brilliant that he basically got the whole thing going. Nature isn't classical, damn it. If you want to make a simulation of nature, make it quantum mechanical, right? It doesn't look so easy. That is the understatement of the century, frankly. Next. Okay, brief history of quantum computing. Okay, so you're talking back in the 20s. People were struggling with the atomic physics even earlier, right? 1926, Schrodinger and Heisenberg got their equations going, matrix equations, wave equations, right? And of course there was, anybody know anything, any of you taken a course in quantum mechanics? Anybody? A few, very few. Well, sort of quantum mechanics is, I mean, I've been studying quantum mechanics a long time. It's still pretty amazing, right? It basically clashes with our sort of intrinsic view of reality, which is things happen locally, everything happens locally, there's a cause, there's an effect, and so on. Right? Einstein was really bothered by what he saw coming out of quantum mechanics. Bohr, who was his famous, I guess, anti-hero of Einstein at that time, basically would say, nah, don't worry about it, just compute, right? But Einstein was really bothered. So in 1935, he wrote this famous paper called "Something is Weird If It's Really True that Quantum Mechanics is the Full Description of Nature." And they didn't at that time have any idea whether that was the case or not. Then you have a problem that you have basically, quote, faster than speed communication or action at a distance. Spooky action at a distance was Einstein's phrase, right? That was probably Einstein's last great contribution to physics, actually. It was theoretical because at that time they had nothing, they really didn't make any difference to sort of computing the energy levels of hydrogen and all of that kind of stuff. There was an Irishman by the name of John Bell, 1964. In his day job, he was an experimental particle physicist. But in his nighttime, he worried about the foundations of quantum mechanics. He said it's not a theoretical thing, right? Because actually, he developed a set of equations called Bell's inequalities, which have since been improved using other kinds of approaches to this. But at the time, they were sort of a big breakthrough and said, we can actually test for this stuff, right? We can actually test whether Einstein's worry is justified or not. And that kind of led to the slow growth of the basics of quantum mechanics, which eventually led to the theory of computation in quantum mechanics, right? In the 70s, people started looking at what a quantum computer would look like theoretically, right? Things, for example, like classical as in the computers we have today, you can easily make a copy of a bit, right? Nothing could be more trivial, right? The problem was in quantum, there's this thing called the no-cloning theorem, which is you have a quantum bit, you can't just make a copy of it. It's much more complicated than that. So there was all these sort of generalized rules that were developed about what a quantum computer would look like, right? We mentioned before in 1981, the first conference on physics, you just saw the pictures, right? You can see there, by the way, all of the blue, the ones that are filled in here, like this one, not this one, it's hard to see in this black and white, it should be much easier to see. But the ones in light blue are basically where IBM was involved in this, because from the beginning, IBM had been very heavily involved. Back in the 60s and 70s, IBM was a dominant computer system, right? So clearly they had the resources and so on to sort of contribute to this. Discovery of topological quantum order in 1982. That was led to a Nobel Prize in Physics, I think, 2 years ago, right? Quantum cryptography. People have heard the concept quantum cryptography, right? How you use a quantum system to basically develop a whole sort of quantum cryptographic system, right? And of course you can actually, you know, there's actually quite a bit of business now, and the reason why there's quite a business in this is that quantum mechanics, quantum computing is a threat to many of the known systems for encryption that we use, right? So what's actually happened because of that, you can actually develop new algorithms that are called post-quantum encryption, right? So you're replacing the old encryption systems we have by ones that are much more robust, based on lattices and so on and so forth. Very active area of research. Quantum teleportation, people know what that means? Basically means you can teleport a bit, not quite Star Trek yet. We have another 10 to the 23 improvements to go, or 10 to the 35 or whatever. But it literally means you can teleport a bit from one spot to another spot, right? The thing that really got everybody going was Shor's factoring algorithm, because it's easy to multiply two big numbers together to make a huge number, right? But factoring two huge numbers, I think it's fair to say that the complexity of that is sort of unknown, but practically speaking, very difficult, right? So the reason why our encryption algorithms today are safe is because we don't know how to factor two large numbers. Shor came along and said, basically, if you have a 2,000 bit by 2,000 bit multiplication, and you have a quantum computer that's 2,000 bits, you should be able to factor that system. So that got everybody very worried because, at least not very, very worried, but it was an interesting kind of bow to, oh wow, what else can a quantum computer do? It really had a phenomenal impact on what are the possibilities associated with quantum computers, right? Quantum error correction, I mentioned before that this is 1995. That, you know, copying a bit is pretty easy. Not only that, doing error correction in classical computation is very easy. That's basically what my group does. For example, when you're doing encryption and decryption, you want to make sure you don't lose any bits, so there's no issues with it or noisy or whatever. So we do a lot of error correction, for example, to make sure that when you encrypt and decrypt something, it stays stable, right? Then there was, later on, 1996, there was a guy called DiVincenzo who put together DiVincenzo's rules for what it would take to build a quantum computer, a certain error rate and so on, right? What are the characteristics of what it would take to build that? And basically, those are sort of the guiding principles of what people use today for quantum computers, okay? I mentioned afterwards topological codes. Topological codes are basically an approach that is now developed in this huge theory of topological codes on how you would do quantum correction for quantum bits, okay? Where were we? Just to put it in context, 2001, state of the art was factoring 15, right? 15 equals 3 by 5. Wow. Okay. A significant breakthrough, and I'll talk a little more about circuit QED. This is an important time to sort of talk about how quantum computing is structured. You have obviously the physical computer. You have all the electronics that control that physical computer. And then at some point you get to the actual algorithms. The algorithms for quantum computing are independent, of course, of the physical infrastructure below, right? So if you look at the industry today and all the funding that's going into the industry, there's probably 6 major approaches to doing actual quantum computing. NMR, different approaches. There's a company called IonQ that's using ions. Google and IBM are both using what's called circuit QED, right? So basically, people were trying all sorts of different approaches, but none of them had the right characteristics until circuit QED came along in 2004. And to be honest, the approach that people are taking is still undergoing transformation. They're looking for a set of characteristics that have the perfect set of characteristics. I just want to put this in context that when silicon came along, you know, silicon was competing with germanium. It took a long time for silicon to show its absolute superiority over germanium. And then obviously germanium died out and silicon became the dominant. The other thing I want to put in place is in context, right? We don't fully understand a lot of aspects of quantum mechanics today. And just to put it in context, Einstein did his general theory of relativity in 1915, and we discovered the first gravitational wave in 2015. It took us 100 years, right? Black holes. When was the first projection of a black hole? The first idea of a black hole was what year? We just saw the images last week, right? First hypothesized in, anybody want to take a guess? 40s and 50s? 1784. John Mitchell, an English physicist, said, because at that point they could calculate the escape velocity of a theoretical rocket escaping from the Earth. In this case, said, hey, what if you have the speed of light? How big does it have to be? And he called it, interestingly enough, which I think is a great name, dark star. It's a beautiful name, right? So my point is, this stuff takes a long time. There's another example I will give you, which is fusion. Fusion has been talked about since the 50s. Here we are, 2017, we're 70 years later. And by the way, there's tremendous progress being made in fusion now, finally, so who knows, right? My point is, we'll talk later on about where quantum computing is. The answer is, nobody really knows where it is. It requires breakthroughs. But again, I'll remind you one more thing to keep in mind in terms of timing. 47, the transistor was invented, right? 62, IBM used them. They were the big user of transistors in the world. 62 was when they first used them in an IBM system. It took 15 years just to be able to get them into a system, right? Nowadays, of course, 20, 30 billion transistors is nothing, right? But that took millions of people working for 50, 60, 70 years to get it going. Quantum has had nearly nothing like that kind of support, right? Doesn't mean it's going to be a barn burner when it happens. It doesn't mean it's going to be a failure. It's a question of how much effort you put into it, right? I mean, you look at a guy like Elon Musk, who's transforming so many industries simultaneously because he believes he's sending people to Mars. Nobody thought that would be possible for quite a while. Part of what's going on, again, post this circuit QED in 2004 is coherence time. Coherence time is basically if you have a bit that's, say, in a 1, how long do you wait before it decoheres to what's called a 0? Now, in my business, we compute the reliability of a transistor. What's the average lifetime of a transistor? 100 million billion years, the average transistor. It lasts a while. Current state of the art for a quantum bit is millisecond, yeah. We have a ways to go, right? However, it doesn't have to be a billion years, right? It just has to be good enough, which is if you're involved in a computation, you're sweeping through in a computation, it stays coherent long enough, it stays in the right place long enough that you can actually do a computation. And by the way, since 2000, this number has gone up by 10 to the 5, right? So you look at where its situation looked in 2000 versus today, in terms of just coherence time, this is for a single bit now, just for a single bit, 10 to the 5 improvement. So the naysayers is like, well, be careful, not so sure, right? It's a tough road, but don't be so sure. The improvement has been unbelievable, right? A demonstration of simple error correction, for example. This is when IBM made quantum computing available to the world. I hope some of you have been there. We'll talk a little more about that later on. And then IBM launches commercial universal quantum computing. Okay. Took a while on that chart, but it basically summarizes where we are. Okay. Okay, everybody knows about bits, right? The interesting thing about it is that if you look at, let's say, quantum chemistry, everybody's probably, looked at or thought about, has heard about chemistry, for example. Very complicated topic. Caffeine has like 160 electrons. When you start talking about the computations around 160 electrons, forget about it, right? Now, scientists have been pretty clever at converting, if you did have, let's say, a quantum computer with 160 bits, you can convert it to what's called effective Hamiltonian. Effective Hamiltonian is a description of, let's say, the caffeine molecule. And from that, you can compute things like the energy levels and so on, and make improvements or whatever you might want to do with caffeine other than drink it. Okay, next chart. And likewise, if you go look, let's say, the penicillin, right? Classically computer, this is about where we are now. A biggest supercomputer in the world, which was basically taken over by Oak Ridge last year, an IBM machine. it's of the order of 10 to the 48 bits, right? Massive machine. That could be, in principle, for the kinds of problems we're talking about, be done by a 140-bit quantum computer. All right? This obviously, we're reaching the kind of upper limit of these kind of numbers, 10 to the 48. We're doing, exascale for the first time. This machine is the first integer exascale machine, right? And it would struggle to do a caffeine molecule, okay? So the question is, can quantum do it? That's an interesting question. Okay, next page. I think you get the idea. Total bits on the internet, 10 to the 25, right? 116 bits to model naphthalene, right? Classical bits required, more than we currently use. In other words, factors of 2 kill you pretty quickly, right?
What do you mean on the internet?
The number of bits stored on the internet is 10 to the total bits, right? Okay. Okay. Next. Okay, exponential growth, right? When you have a quantum computer, you basically, instead of 1 and 0, you have 2, you have a base 0, base 1, you're living in between. It's a combination of state 0 and state 1, A and B. Next page. Yeah, obviously, you can start to see once you have like 8 bits, right? Things can happen and get very complicated very quickly. Okay, keep going. Okay. 280-bit computer, 2 to the 280 would be more than all the atoms in the universe. It's not necessarily an apropos comparison, but just to kind of give you an idea of scale, right? You quickly run out of room for doing lots of problems, right? Okay, next. Anybody taking courses in complexity theory? I assume some of you have. Yes? No? Okay, one person. Okay. Complexity theory. If you want to sort n numbers, high to low, how many operations does it take? Petrus, I'm sure you know.
In log n.
Okay, excellent. Some people have taken courses in complexity. That's kind of the lower base. Traveling salesman is what?
NP.
Yeah, it's n factorial basically with a couple of whatever, right? In other words, these are the hard problems, right? This theory developed basically in the 50s, 60s, and 70s into categorizing in computer science how hard problems were. The last time I looked, I believe it was Scott Aronson out of MIT. He has a map of complexity classes. You know how many complexity classes are currently recognized by Scott Aronson? This shows 3. Scott shows 755 last time I looked. Okay. Now, in the middle of this is quantum, right? Quantum will not be able to do all the hard problems, but there's a lot of problems that quantum in principle should be able to solve. So we call them, quantum speed up problems, right? For some examples where we know for a fact it can speed it up, like Shor's algorithm, and there's other ones where we simply don't know where it belongs, right? Okay, next. So, where do we think we can go with a quantum computer? Now, obviously, this is dependent on how quickly one can build a quantum computer. Let me just say that, as I said, there's competition. There's a company called IBM Q, which is using ions trapped by magnetic fields. There's a company called D-Wave. Anybody heard of D-Wave? D-Wave, as you probably know, is not a general-purpose computer. It's basically a quantum annealer. You basically let it find its own minimum. You don't try to control what it's doing. They don't have to worry about errors. They don't do any correction for errors. They're up to 2,000 or 4,000 bits already. Question is, can they find a marketplace? And they may very well do. And then there are companies like Microsoft, IBM, Intel, Google, who are putting a lot of money into quantum computing, right? The other thing I will remind you of that there's a National Quantum Computing Initiative sponsored by our government, which is now, I think, $1.5 billion. And the biggest country investing in quantum computing is where? China. Somewhere between $8 and $10 billion, right? Huge program. Huge program. If you look at the papers being published, there's a lot of publications on quantum coming out of China. Okay. So in principle, you can look at some of the difficulties that people are having now that quantum computers could solve. Again, I You can look at these. I'm not going to go into anything in particular, but molecular modeling we talked about, optimization, portfolio management. I'm never quite sure I understand that one. But there have been papers published, for example, the financial services industry, the financial industry. When you're doing risk assessments, you do Monte Carlo, right? Anybody know what Monte Carlo is? Okay, you run things lots and lots of times. You get a distribution, you assume a distribution of all your variables. You run all your variables and get a distribution of the whole damn thing, right? And then you do risk management or whatever it is based on that. You know, you can prove, for example, that a quantum computer, if it's big enough, can do Monte Carlo a lot more efficiently than a regular computer, right? So there are limited but real examples of where quantum has the potential to be very interesting. All right, talk a little more about that as we go on. Next. Okay, 2 papers published by IBM. One was chemical potential, I think it was lithium hydride or beryllium hydride, I forgot, maybe both, beryllium hydride, I think. Another one was on AI, right, in Nature. I've read this paper, very interesting. I recommend if you really want to see what quantum computing can do, read that paper in Nature. That one I haven't read yet, but again, I mean, it's interesting to see what people are doing in terms of state of the art. Next page. Okay, so I talked about some of the fundamentals of quantum information science, cryptography, cloning, and so on, right? Create and scale bits with increasing coherence. I did mention 10 to the 5 bits. Now, I should emphasize that single bit coherence is considered a solved problem. It's good enough for what we need. The next step, and where a lot of resources are going into, is controlling 2 or 3 bits together, right? Making them cohere together, right? Instead of being 99.9, it's more like 98.5, right? Now, it's come a long way, baby, but that's probably in terms of doing hyperscale integration of quantum computing. But once you get to 99 point whatever, it gets very interesting. Does anybody know what the sort of availability of a modern, let's say, mainframe is? 99.9997, let's say. It's pretty good, right? We have a ways to go, right, for a quantum computer. But as I emphasize, 10 to the 5 improvement in the last 18 years. We are not quite there, but we're not that far away, okay? Core algorithmic development, okay? So has anybody ever looked at some of the algorithmic opportunities out there, right? If not, I recommend you do that. It's an interesting to look at them. Increase in quantum volume. Quantum volume is a very simple metric that IBM uses that basically says a few bits is no good, but lots of bits with lousy error is no good. It's the combination of lots of bits with a low error rate gives you what's called quantum volume, and is an approximate metric of how good your system can be. Clearly things like topological density in terms of intermix of the bits and so on clearly plays a major role, right? Standardized performance benchmarks, that's kind of ongoing. System infrastructure and software enablement. IBM has put a lot of work into this, not just us, but Google and whatever, but I think it's fair to say that at this point, IBM has an actual lead, right? They've gone open source, which is why we saw the discussion about Qiskit later on today. Maybe, Lauren, at this point, you want to just say a few more words. Not everybody necessarily heard what you said.
Sure.
Why don't you come on up and just...
I also want to add a couple other resources that are useful. Let me get in front of the camera
Sure,
and then I'll
absolutely.
talk. So, hi everybody, hello again. So I already pointed out Qiskit.org. There's a ton of information there, basically IBM's community and ways to start to visualize and think about qubits. The other resources that are useful, there's, and I don't remember the URL off the top of my head, but if you Google Quantum Zoo, there's a list of algorithms, which is working on this.
Quantum Zoo is Coherence, I believe, right?
Oh, is it?
Yes.
I didn't know that. But there's a list of things that people think will be productive in quantum computing. They haven't solved them, they're open questions in algorithm design. The other one is Quantum Open Source Foundation, QOSF.org, and they have a bunch of interesting open source projects if you're interested in doing some coding you can check that out as well. So those are the resources I know of.
Yeah. I mean, the reason IBM and the reason I'm here is to encourage people to participate in the open source development of quantum computing, because we recognize it's a huge area of endeavor. We cannot do it on our own. But I will tell you that as potential computer science majors, right, maybe you already are and you're graduate students, there's tremendous possibilities, theoretically, for example, for big breakthroughs in quantum computing, which is why we're here talking to some of the best and brightest minds in the country, because we want you to go and create these quantum algorithms, right? Not just for, I mean, they're open, they'll be open source, but the potential is there. You can go play, you can go work the theory and actually run either quantum simulations or actual, on the real machine, right? So we encourage everybody, if you're thinking about it, get involved. We'll talk a little more about that later on, okay? Now, where are we today? IBM, we're somewhere here today. Different companies are at different places. Microsoft is putting a lot of effort into it. They're using topological computers. So far, the biggest one they've developed, and doesn't mean it's the future, is Zero, because it's an unbelievably hard way, the way they have proved, the way they have chosen. The reason they've chosen is there are built-in advantages to it if they can make it work. They haven't yet, and they recognize that, right? I think if you look at what Google is doing and what IBM is doing, we're basically using, I said, what's called circuit QED, right, as our approach. Where are we today? We're somewhere in between. We're on the fringe of what we call the quantum advantage. The quantum advantage is where you can actually see real-world work being done that is useful to business, to chemistry, to pharma companies, to investors, that you could not do on a classical computer. Now, if you knew precisely when that was going to be, you could probably make a lot of money by shorting or investing in the right companies. But there's no algorithm for that, folks, so you're going to have to take your guess, right? The 20s is when it's going to be, a lot of people think, right? Now, the world is divided into skeptics and people who totally believe, right? I think we'll let the data speak for itself, but there's already interesting things going on sometime in the next 5 to 10 years, right? We shall see, right? But you could be part of that if you so choose, or you can design better time clocks with your computer skills. I'm just saying, right? Think about it. Next. Okay, let's talk briefly about the quantum machine, right? Okay, you've all seen this. This is the famous zeros and ones. And then you got these rotated, you got theta and phi. So you can describe anywhere on this space, right? Why is this useful? Because instead of just having two options, you essentially, in principle, have any option you want on this space. And then if you play your algorithms properly, you can do an awful lot with this capability. Next. Okay, you heard about superposition. Superposition, a single quantum bit can exist in a superposition of 0 and 1, right? And then there's the famous entanglement that Einstein worried about. Now, entanglement is actually interesting, because for certain things like quantum communication, quantum encryption, entanglement is key. When you say for the standard quantum algorithm, how important is entanglement, you'll get a lot of arguments on both sides. There are examples of algorithms that require entanglement. There are people who say, not so important. And there's even people who say, you don't even need entanglement for quantum computing, right? So it varies a gamut. I think it's fair to say that entanglement is not what drives quantum computing. If you actually look at the algorithms being written, parallelism, extension of superposition, where you can basically initialize a whole bunch of bits in parallel, do a lot of parallel computation, combined with what's called quantum interference, where you basically use the fact that a quantum function is basically a wave function. As you overlap all these different waves, you can interfere destructively and constructively. And instead of out of this mishmash, you get a single bit as opposed to n bits, right? It can get you the right answer because of the magic of the way it does its thing. Okay, next. This is basically saying what I'm saying. You can encode the system implying all 2n of the states parallel, right? So we can move on from the next. Okay, we mentioned the quantum volume. This is just an estimate of how good your system is. Next. Okay, we mentioned before some of the kind of numbers you're talking about, like quantum chemistry, optimization for specific kinds of issues. Years to advantage, less than 5, question mark, maybe 10 to the 15. This is a good benchmark. Shor's algorithm, I mentioned before. This is where a fully functioning 2 to 4,000 bit quantum computer, 10 years, maybe. So there's a lot of investment going on. It's clear we need breakthroughs, right, to really make mass production of quantum computers possible. But even still, we can do things with, for example, a hybrid model of quantum computing, which is you use your classical model, then you run into a roadblock of one specific part of your algorithm. You may recognize it as being amenable to treatment by a quantum computer, and we'll show you later how you can just hook it up basically to an ancillary quantum computer and let it rip. Okay, next. Okay, anatomy of a quantum computer. Okay. This baby is a rock star. I have to tell you, I go to conferences and people come up and says, my girlfriend said, I had to come see this. Can you take a picture of me with this computer? Right? It's funny, and I'm talking about dozens and dozens of people at any particular conference. It's a thing of beauty when you actually see it, the way they structure it, right? And the point I want to make is down here at the bottom, you actually have a superconducting quantum chip. Does anybody know how cold it is? If so, don't answer. But if you don't know, do you want to hazard a guess? Nobody's answered. Okay.
Something like about
3 Kelvin? Okay, good answer.
something maybe below.
Below?
Half of Kelvin.
Well, with 3 Kelvin, you can get it has helium-3,4 in the middle here to kind of cool it down to 3 Kelvin. But to really get it work, we don't have too much quantum noise. You have to get to 10 to 15 millikelvins above absolute zero, right? It's an impressive piece of technology. So this is what the baby looks like. This is like a 5-bit, right? This is what a PCB, printed circuit board, looks like. 15 millikelvins, right? So I think there's a better description on the next page, if I'm not mistaken. Go ahead. Yeah.
You'll save another shameless plug. You can actually go online and program this actual machine.
Absolutely. You can actually program this actual machine. Absolutely, right? You can get credits from IBM. And what's shocking to me is the number of people who have done that. We'll show you that in a second here. Right, but this is what it looks like. Now, this is like the current version, room temperature, right? The control stack, FPGAs, radio frequency sources, amplifiers, switches, and all that stuff, right? Because what you are going to be doing is generating an incredibly accurate shaped microwave pulse. Because you're going to generate a room temperature and send down with almost no noise to a system that works at 15 millikelvin, and make sure you don't heat it up while you're at it, right? It's a pretty tough thing to do. This is why it's taking so long, right? But the point is, once you learn there, you'll never forget it, right? The input modules, the input module, the output module. Likewise, when you're reading, you get this pulse out. You then have to amplify that pulse, and then get it read by standard electronics. Okay, next page. All right, this is what the baby kind of looks like. I won't go into this. It's called a superconducting microwave resonator, right? The theory has been known on and off since like 48. Ravi won the Nobel Prize for his work, but optimizing it for a superconducting quantum bit has been a process that has taken 10, 15 years of optimization and re-optimization. It's impressive technology. Next. Okay, we can skip this one. Okay, next. Now, before we go any further, anybody got any questions before we go to the last section? Yes?
I was wondering what types of algorithms can you run on a computer? Do you use it in a similar way to a conventional computer?
You would never want to simulate run on a quantum computer, which you can do classically, right? So you're always looking for an edge, right? So if you go on to for example, Wikipedia, you'll see a list of unique quantum algorithms like quantum Fourier transforms and all sorts of stuff, right? Shor's algorithm obviously is the whatever. By the way, the quantum community is always looking for real developments, right? So you build up an algorithm out of unique kind of subroutines and whatever. there was one class of problems that were considered very hard classically. Anybody has heard this story? You've heard it, okay. There was a 18-year-old college kid by the name of Yuan Tang. She was given the assignment by Scott Aronson to look into this. And she basically demolished all of the classical ones, and they're not really that hard. So the quantum advantage turned out, unfortunately, to be null in that particular case, because this brilliant lady reset the bar and said, it's easy to solve.
Right. The argument is that the quantum computer showed the path towards this.
Yes, yes, it did. And by the way, I guess it's related to the famous Netflix recommendation problem, right? Personally, I think Netflix's recommendations are terrible, but they're very proud of their algorithm. Okay, so I encourage you all, this is the old approach towards doing interaction with the quantum computer. This is by the leader of the IBM Quantum project. This is Jay Gambetta, right? Yes?
Sorry, so with a quantum computer, you're not programming with conventional programming languages?
Oh, you are. I'm going to talk about that in a second. Absolutely. Well, since you asked, I'll ask now. How many languages do you have to learn to program quantum?
Python.
Python. That's all you need to know. Right? How many people know Python? All right. You're all quantum programmers. Congratulations. I just certified you. Okay? Okay. So what IBM started with was this kind of music diagram, music scales, right? We got H and Z and S and Z. And by the way, there is a fantastic little app called Hello Quantum that you can download on your Android or on your Apple. And it's a blast, right? Because you have to start thinking quantum, right? So it basically wants you to move black and white dots to one place to another using only quantum gates. And it's not like move it over here. No, you got to do this twisting and turning. It's weird, right? Which reflects the reality of quantum computing, right? Quantum computing has tremendous potential, but it ain't like standard classical computing. You have to think differently. So it's a fun, for at least an hour, amuse yourself by downloading a little quantum. Okay. So this is what it looked like. Now, this was like version 1, right? And what IBM has done, they've basically they're developing a lot of capabilities. They're not the only ones, but I think most people recognize that IBM is further ahead than most in terms of quantum experience. Go to the next page here, right? Okay, it's called Qiskit. Lauren mentioned it earlier. It's hard to read the details here on this one because of our poor resolution. Let's go ahead to the next one. Okay, so there's different parts to it. The hardware, of course, you've talked about, right? Terra, Qiskit Terra, foundational tools to build and compile quantum circuits. You know, it's a lot of the stuff like controlling microwave pulses and doing all this sort of gory gorp that you as programmers may not be interested in, but some people could be interested in, right? Ignis, tools for characterizing and mitigating error. For example, if you're getting errors, you can actually look at the error rates that come associated with, you know, if you're using bit A and B, you can look at the errors, and then you can do things like subtracting the errors because they're known systemics in the system, right? So this will help you with those kind of mitigating factors, right? AIR, special purpose simulators for algorithmic development, right? So obviously people want to use the machine, but a lot of the time you're better off using a simulator, right? Getting ready for while you're debugging, then getting ready to actually use it on a machine. And here, Qiskit Aqua, framework and libraries of quantum algorithms. I think that was your question earlier, right? Libraries of quantum algorithms that allows users to leverage quantum computing efficiently, right? Okay, next. Software stack, I think we talked about it. Terra, Aqua, Ignis, and AIR. Does anybody recognize them as other names? Huh?
Elements.
Yes, are you Indian? Yeah, the 4 elements, right? Fire, earth, water, and so on. Okay, next. Okay, so this is Q5 Tenerife, or Tenerife, I guess. This actually shows you where the frequency at which it operates, 5 gigahertz. T1 and T2 are the coherence times. I talked earlier about coherence is when you have the different kinds of ways a bit can lose its coherence. Coherence being, for example, it drifts from 1 to a 0. So this just gives you an idea in microseconds, 52 seconds. The bits, you can see quite a bit of variability in the bits, 52 to 48, 61, right? It gives you an idea though of the kind of error rates. Here you can see the error rates in 10 to the minus 3, so it's 99.5, right? This is an older machine, I mean obviously they continue to get better. This is a 5-bit machine, state of the art now is a 20-bit and then even possibly a 50-bit, right? I think Google's Bristlecone is 70-ish kind of number, right? Okay, next. Oh, go back 1 second here, I want to just say, the challenge here is multi-bit gate errors, right? As I said, they're 98, 98.5. That's where a lot of the focus is. If that gets above 99.5, all bets are off, right? If you could, because then you can get really serious about large quantum systems, okay? Okay, hybrid approach. So for example, you're doing your classical means the stuff we do every day, right? Classical processing, all of a sudden you run into something, so you borrow your quantum algorithm, and really nothing could be simpler, as you'll see in a second. Okay, a little more. You can see how it would do it, right? You can see basically set up, measure, iterate, generate a new wave function. That's typically how you do a lot of kind of quantum analysis. Okay. IBM Q experience. Let's go to that. Let's talk a little more. So, time to build a quantum community. Basically, IBM wants to do that. Anybody can play with a quantum computer, right? I think the next page, go ahead. Let's go one more. Here's what's interesting. 100,000 users. How many people here have used it? 3. Okay, good. All 7 continents, including Antarctica. 6 million experiments. I bet you guys didn't know that, right? 6 million experiments, right? 125 research papers. People are doing publishing. Of course, obviously, a bunch of them are IBM, right? This gives you an idea of kind of what's going on here. Like, obviously not surprising. That's probably like Oak Ridge. They have there's a lot of activity there. But I don't know what university would that be? Huh?
That looks like Champaign Urbana. It's not Chicago. Chicago's up there.
Chicago's up for over there, yeah. So it's interesting to see. So you can use a 16-bit computer or a 5-bit computer, right? These are actual executions on a real quantum computer, not simulations, right? Okay. Okay. The titles are interesting. Bayesian deep learning on a quantum computer, and so on. Next page. Cloud quantum computing of an atomic nucleus. Quantum risk analysis, Monte Carlo. Okay. You haven't seen this one? Vitalia, it's great. I think the last time I looked, it had like 500,000 views. I mean, how many people watch videos on quantum computing, for God's sakes?
It's a great introduction. It talks to you
Absolutely.
From grade school all the way up to a grad school student understanding of how quantum.
She goes through the 5 levels of understanding, but it's a blast. It's fun. Okay. Next, the IBM Q network. Okay. So accelerate quantum research, develop commercial applications, and promote, educate, and prepare for the new quantum age. Now, very clear, IBM is not saying this is going to replace standard computers, right? But it may be, because we know today, Moore's Law is dying on the vine. I mean, I had a good long run with Moore's Law, right? We went from 1 transistor to 28 billion. We're not going to go to 300 billion. It's not going to happen, right? We've run out of gas with Moore's Law. So if we're going to have hard problems we want to solve, we're going to have to use a quantum computer. Okay, next page. Some of the people involved. I mean, Oak Ridge should be on there, for example. I was down in Tennessee recently. Yeah, there we go, right? They have a very active group. You can look at the names here. So, ExxonMobil, Daimler. JP Morgan is very interesting. How many people you know there's a quantum meetup in New York City? Same 2 guys. Okay, you. Okay. There's a fantastic quantum meetup once every month on Wednesday nights in New York City. I try to go to it pretty much every month. And it's an eclectic mix of venture capitalists. And one guy stood up and said, I'm a Harvard researcher and a venture capitalist, and then sat down. It's like, okay. I don't know what that means, but it sounds interesting, right? And you get a lot of aging PhDs who are now in finance making millions, but they missed their old physics, so they want to be involved. And there's young computer scientists who want to work in the field. It's a good thing to kind of get involved. And the topics are at a very high level. Microsoft was there a few weeks ago, IBM was there. Guys building optical quantum computers, come and show their stuff. So it's very interesting. I highly recommend you can't miss it. Quantum computing meetups, New York City, right? Next. Okay. The driving advancements in quantum software and algorithms, right? Simulating quantum systems, artificial intelligence, optimization, Monte Carlo. Usually what this means, if you can describe a Hamiltonian, this one, if you know what Hamiltonian is, right, then you can basically go to work with a quantum computer. Okay. Next, quantum chemistry, we've talked about some of these things. Pattern recognition, risk analysis, Monte Carlo. Okay, next. The hubs, I mentioned that Oak Ridge would be very important, for example. Deep collaborative research and applications utilizing IBM Q, right? Members, and then workshops and resources, right? And this kind of outreach like I'm doing here. Okay, next. Okay. ExxonMobil. Right. State-of-the-art computing research using IBM Q technology. Okay. Next. ExxonMobil. Okay, how to get quantum ready. This is more relevant to you guys, right? Discover more about it. This is a picture from the old one, but I want to emphasize QuizKit, right? Download QuizKit, and all you have to worry about is Python. And so if you want to learn Python, why not kill two birds with one stone, right? Learn Python by quantum programming, as opposed to calendar number 5,841, right? Okay, collaborate and so on through the IBM Q network. Okay, next. IBM system, this is our state-of-the-art Q, system 1, right? This is the little baby that goes into it. This is what it looks like, right? And basically what it happens is, as you go down through these coils, you're getting colder and colder. So by the time you get to here, you've got helium-3 and helium-4 cooling it down to 3 Kelvin, I think what you said earlier. By the time it gets down here, it's 10 to 15 millikelvin. Okay, next. That's what it looks like. This is the newer version of it, right? Quantum One. Okay, next. I think that's it. We're done, ladies and gentlemen. Questions? We're 10 minutes over, but the pizza was at least 7 in there.
We do have more pizza, so in case anyone
Okay.
wants any more food.
Yes, sir.
Questions.
I'm very interested to hear more about sort of why in quantum chemistry there's such an advantage here. I mean, on your graphic you showed sort of quantum chemistry advantage at the top and then finite element method at the bottom. Coming from a numerical PDE background, that's very counterintuitive because to me, quantum chemistry is the hardest PDE. So can you talk a little bit about that?
I think I'm not going to give you necessarily a good answer. I think part of it is because there's a well-developed process now for converting Hamiltonians into quantum effective algorithms. I think that's part of it, right? It's probably based on interest. It's probably because there's a lot of academic research going on, as you probably well know, in terms of quantum simulation of chemistry, right? I don't have a good answer because in principle it could be very complicated very quickly, right? Penicillin is so outrageously complicated, right? Proteins are so outrageously complicated, right? So I don't have a good answer except academics must have attacked it first, right? Lots of accidents of history. Yes, sir.
The problem John Presco's working on?
Pardon?
John Presco's working on?
Is he working on quantum chemistry as a focus? I mean, you probably, I've read a lot of his stuff, but I don't,
So if you go in an archive, if you look up John Presco, he shows the path that they're trying to take this one.
John Preskill is one of the guys who's really gung-ho on quantum, right? Okay, yes, sir.
I had a basic question. A conventional computer
Yes,
saves a bit as a voltage level, right?
yes.
How does the quantum computer save us Superposition.
Well, it's an oscillation that's going on all the time. So you're reading a certain frequency or phase associated with that. And when you want to read it, basically just like anything in let's say a cavity, a photon just oscillates in a cavity until it hits something and then doesn't go, right? So there's certain life associated with an element. In the same way, you just get these oscillations that go on until something crazy happens, right? Like that's where you get into what's the coherence time, right? You hit an imperfection in the cavity wall, you hit thermal noise, you hit whatever, right? Okay, question. Yes, sir.
How does IBM plan to deal with the emergence of photonics-based quantum hardware?
Okay, so I'm not here to bash anybody else, but photonics is a very, very tough road as a quantum computer, right? I mean, I think there's 6 or 7 different methods of which photonics is one, right? And it may be that somebody proves me wrong, in which case, great. But I think photonics is about the toughest of all the ones they're trying to do. You may have a different opinion. What?
You think it's harder than topological?
I actually think the topological in the next 10 years might kind of come through. I mean, this is me speculating. I'm not the expert. I've read a lot on both photonics and quantum. In fact, at the meetup in quantum about 2 months ago in JP Morgan, they had a gentleman come in and talk about photonics, and it's a tough road, right? I mean, I said, like, what sort of photodetector sensitivity do you need? You need to be able to detect a single photon. He said, we're about 13,000 now, so they've got a long way to go to get it down, right? Encourage all the experiments, because we don't know ultimately what the right answer is. I think a large group of people have decided that some form of quantum electrodynamics, circuit quantum electrodynamics, is the best approach. But I would definitely not eliminate topological. And certainly one of the dark horses is IonQ, right? That's part of the thing is the algorithms are independent of the underlying structure, okay? We're done? We're out of questions? Go ahead. Sorry, I'll get you next. Yes, sir.
So are classical simulations with quantum mechanics very important to design technology? I mean, are you using?
Well, I think you can use them as toys, right? Until you get to the point where you need 1,000 bits, then forget it, right? Unless you can get time on Oak Ridge for the next billion years, right?
It's actually a great question once you get over 100 bits on the quantum computer.
You can't do it.
How do you prove that your answer is right?
Yeah.
Because you can't simulate it classically.
Right.
But I mean, in actually building these devices.
Oh, sure.
Is there a back and forth between the simulation and the experiments that uses density functional theory? And maybe not density functional theory.
From my perspective, what's more interesting is you can test your algorithm now.
Right.
So you can, if you're a programmer and you write an algorithm, you can test it on a simulator up to 30-some bits now. Whereas the computer, the actual physical hardware can't manage that.
Because 30 bits is kind of way short of a supercomputer. Once you start talking 40, now you're talking about serious engineering resource. If you're interested in quantum chemistry, you have to read that first article I showed you in Nature. That really explains a lot about how they do Hamiltonian conversion, kind of approximations they make, and imagining what one could do with a 50-bit version of that same kind of capability.
And there's a great error mitigation paper that just came out where they are using this new error mitigation technique to almost exactly match the theoretical physical characteristics of the molecules.
You wanted to ask a question?
Never mind.
You don't? Okay. Anybody else? Yes, sir.
This might be basic, and I might have some.
There's no such thing as basic when it comes to quantum computing. Sorry.
Okay. So most of the algorithms you mentioned that we can give it a try are assuming that the quantum computing works where you use qubits and you can run everything in parallel and
yes,
you don't have those problems. But if I understand right, you have qubits and then you have a gate or a filter which converts those qubits to specific discrete values like zeros and ones. I mean, qubit can be.
You mean when you do a measurement?
Then do a measurement.
The measurements are 0 and 1. We didn't talk much about measurement theory around quantum mechanics. It's been, people have been talking about multiple realities and so on associated with quantum measurement, the quantum collapse problem for the last 100 years. It's like you could write multiple PhDs. Anybody heard of the, not the multiverse, but the, what's the name? basically Everett's theory of multi-universes. Many worlds, thank you, that was the correct word, right? Basically, every time you look at an electron, you just create a whole new universe. It's like, really? Okay. But there's some strange things that go on we don't understand in quantum. So very strange things, right? Quantum computing's approach is, don't worry about the philosophy, just use it, right? Okay, did I answer your question?
Yeah.
Okay.
My second follow-up question was,
Yes.
so as a computer scientist, can you do anything like, if you don't have any background?
Can you do anything what?
Can you work on measurement further developing what we understand on?
Absolutely.
A resounding yes to that.
Yes, yes. The answer is yes. The future belongs to this crew and all the other crews and all the computer sciences universities around the world, right? There's nobody in this world who knows what the limit of quantum computing is until people go work on the hardware, on the algorithms and everything else, right? Who would have envisioned when Bardeen went home to his wife in 1947 and said, it was a pretty good day today? He could not have foreseen 24 billion transistors on a chip. He was worried about the one he was measuring in his lab that day, right? We don't know. The future belongs to you guys.
A lot of the really exciting work that's going on right now is in compiling and writing a really efficient compiler
Yes.
for the quantum computer.
Right.
So you don't need to know any quantum mechanics at all. You just need to be able to write a compiler.
If you write an algorithm that the compiler looks at and goes, it's not really the most optimized, it'll try to optimize it for you because it's a resource scarcity, right? So they're trying to write better compilers to be more efficient,
Yeah.
right? That's a whole very active area. There's so many areas of active research. I mean, as a thesis project, or as I said, instead of writing another, silly little thing, do something substantial. See how far you can get. That's my recommendation. Okay, anybody else? Ladies and gentlemen, I think we've reached the end.
Thank you.
There's more food. Feel free to hang out for a bit afterward. Thanks for coming.
Yeah, just enough seats for the crowd.
Just